In the history of paleontology, no creature has undergone a more radical or frequent transformation than Spinosaurus aegyptiacus. For over a century, since its first discovery in the Egyptian desert, this sail-backed giant has been the ultimate enigma of the prehistoric world. At various points, we have envisioned it as a bipedal version of a T-Rex, a quadruple walking river monster, and a sleek, penguin-like pursuit predator. But, as we stand in early 2026, the scientific community is embroiled in what many are calling the Spinosaurid Civil War. A series of high-stakes studies released between 2024 and late 2025 have shattered our previous certainties, pitting high-tech physics and machine learning against one another. We are no longer just looking at a dinosaur. We are witnessing a masterclass in how modern technology forces us to rethink the very nature of extinction. This is the story of how the latest breakthroughs have turned the world's largest carnivore into the most controversial animal to ever walk, or swim, the Earth. The narrative took a dramatic turn in early 2024 when the prevailing image of Spinosaurus as an aquatic pursuit predator began to crumble under the weight of fundamental physics. For several years, the scientific world had been captivated by the idea of a dinosaur that chased its prey through the depths, propelled by a paddle-like tail and weighted down by exceptionally dense bones. However, a landmark study led by Paul Sereno and Nathan Myhrvold, published in the journal PLOS One, forced a total re-evaluation of this lifestyle. The researchers utilized sophisticated three-dimensional digital models to test the stability and buoyancy of the creature in a virtual river environment, and the results were a stark departure from the movie monster imagery of the past. The primary obstacle to the pursuit predator theory was a matter of basic fluid dynamics and buoyancy. Even though Spinosaurus possessed dense bones, the sheer volume of its internal air sacs and massive lungs would have acted like a biological life jacket. The study demonstrated that the animal would have been incredibly buoyant, floating persistently on the surface, rather than sinking gracefully into the depths like a penguin or a seal. Furthermore, the center of gravity and the center of buoyancy were positioned in a way that made the animal inherently unstable in deep water. If a Spinosaurus had attempted to swim rapidly or dive, it would have been prone to rolling uncontrollably onto its side. This lack of stability meant that the predator could not have executed the high-speed underwater turns required to catch agile Jurassic fish. Beyond the issues of buoyancy, the researchers also attacked the statistical foundations of the bone density arguments. They argued that the previous analysis used to link bone thickness to a diving lifestyle was mathematically flawed. By expanding the dataset to include a wider variety of modern animals, they showed that heavy bones are not exclusive to divers, but are also found in massive land animals like elephants that need support for their immense weight. This led to the emergence of the Hell-Heron model, portraying Spinosaurus as a semi-aquatic ambush specialist. In this version of history, the giant stood in chest-deep water with its flat-bottomed feet firmly anchored in the river mud. It likely remained motionless for hours, using its long, sensitive snout to detect vibrations in the water before striking downward with the speed and precision of a massive wading bird. While the debate over biomechanics raged in the journals, the late months of 2024 provided a physical breakthrough from the sands of the Sahara. At the annual conference of the Society of Vertebrate Paleontology, Paul Sereno unveiled the remains of a previously unknown species of Spinosaurus discovered in Niger. This discovery was profound because it proved that the Spinosaurid lineage was far more diverse and geographically widespread than anyone had anticipated. This new specimen was not merely a copy of the famous Egyptian giant, but possessed distinct anatomical features that suggested a completely different evolutionary path. The most striking feature of this Nigerian predator was the shape of the crest on its skull. While the classic Spinosaurus aegyptiacus is known for a relatively straight, rectangular crest, this new species featured a crest shaped like a scimitar. This curved, elegant arc of bone served as a clear indicator that these structures were not solely for shedding heat or providing stability while swimming. Instead, the diversity in crest shapes points toward complex social behaviors and species recognition. These crests likely acted as visual billboards, allowing different species of spinosaurids to distinguish one another in the crowded, dangerous river systems of North Africa. The presence of multiple species within the same general region suggests a highly layered ecosystem defined by niche partitioning. It is likely that the scimitar-crested species of Niger and the blade-crested species of Egypt evolved different hunting strategies or preferred different types of river environments to avoid direct competition. This discovery effectively moved the scientific conversation away from the habits of a single super predator and toward the broader success of an entire family of dinosaurs that had mastered the boundary between land and water. It shows that the Spinosaurid blueprint was flexible and successful enough to branch into several distinct forms, each dominating its own corner of the Cretaceous floodplains. Just as the wading bird model seemed to be cementing its place as the new scientific consensus, the final months of 2025 saw a high-tech counteroffensive from researchers at Yale University. This study represented a shift away from traditional mechanical modeling in favor of the burgeoning power of artificial intelligence. The team utilized machine learning algorithms to process a massive dataset of over 11,000 measurements taken from a vast array of modern animals, including birds, reptiles, and mammals, with varying degrees of aquatic adaptation. The goal was to see where the skeletal proportions of Spinosaurus fell when compared to the known patterns of the animal kingdom on a massive scale. To the surprise of many, the artificial intelligence reached a conclusion that directly contradicted the 2024 buoyancy studies. The neural network placed Spinosaurus firmly within the category of primarily aquatic animals, finding that its anatomical ratios were statistically most similar to modern pursuit divers like seals and penguins. The AI identified deep-seated biological signatures in the paddle-like tail, the retracted position of the nostrils, and the specific density of the limbs that pointed to an animal designed for a life of swimming. This created a profound tension in the scientific community, pitting the laws of fluid dynamics against the large-scale patterns identified by machine learning. The Yale study argued that while human-led physical models might suggest the animal was too buoyant, the evolutionary record written into the bone structure of Spinosaurus suggests that the lineage had successfully navigated those obstacles. This debate highlights the difficulty of reconstructing the behavior of an extinct creature that has no perfect modern analog. It suggests that Spinosaurus may have possessed soft tissue adaptations or behavioral tricks for diving that are not immediately obvious through digital physics alone, reinforcing the idea that this predator was one of the most specialized organisms to ever exist. As we move into the research landscape of 2026, the image of Spinosaurus has become more complex than ever before. We are forced to view this creature as a biological hybrid that likely defies our attempts to place it in a single category. The most recent syntheses of the 2024 and 2025 data suggest an animal that was a generalist of the water's edge. It was capable of wading in the shallows to ambush lungfish with the precision of a heron, but it also possessed the power to cross deep river channels and hunt in open water when necessary. The massive sail on its back, once thought to be a swimming stabilizer, is now widely viewed as a masterpiece of social signaling and thermoregulation. In the humid, sun-drenched environment of the Cretaceous North Africa, the sail would have been a vital tool for dumping excess body heat or absorbing the morning sun to kickstart its metabolism. Visually, it would have made the animal appear even larger than it already was, acting as a terrifying deterrent to rivals like Carcharodontosaurus or the massive crocodile Sarcosuchus. The sail was not a rudder. It was a flag of dominance that could be seen from miles away across the flat river deltas. The shifting story of Spinosaurus represents the cutting edge of modern paleontology. We are no longer just digging up fossils, but are stress testing them in digital environments and analyzing them with sophisticated algorithms that can see patterns invisible to the human eye. The research from the past 2 years shows that evolution is not a straight line toward a single perfect design, but an ongoing experiment in survival. Spinosaurus was a masterpiece of adaptation that successfully dominated some of the most dangerous ecosystems in history for millions of years by mastering the boundary between land and water. It remains the ultimate example of how every new discovery can force us to rewrite the history of life on Earth. The legend of the Spinosaurus is far from settled. With every new scan and every new species found in the sands of Niger, the pharaoh of the dinosaurs continues to evolve in our minds. It remains the ultimate reminder that science is not a destination, but a journey into the deep, dark waters of the unknown.